Alright folks, this week we're going to start talking about motion in two dimensions, so this will include projectile motion and a little bit of circular motion. So I'll just go through the examples in the notes. These will include some diagrams, some concepts. They're also going to include equations and working with variables and some things that are kind of new. So this will just be a little bit of an introduction prior to some of the other assignments for this week. So is closely related to free fall, and I know we've talked about free fall in the past where if an object is just dropped from a given position and it's let to fall, when the only effect that it's under, or the only force that's really acting on it is the force of gravity and or any wind resistance or forces that would counteract that in nature. So we've talked about free fall before, where an object maybe just goes straight up or straight down. In order for something to be considered a projectile, it could be traveling in a straight line in a slight arc, or a more solid arc, or it could be traveling maybe launched across in a straight line. So it really doesn't matter that it's launched up or sideways or down. It just, to be a projectile, it has to only be under the influence of gravity. So in these diagrams here, when objects are dropped or thrown into the air, the one acceleration that's always acting on them is the negative 9.8. So objects that start out at rest and fall downward pick up a speed at 9.8 meters per second squared, and objects that are launched into the air reduce their speed at a rate of negative 9.8 meters per second squared until they come to zero, and then they'll fall back to the earth and accelerate just as if they were dropped from this top point and work their way downward. So, for example, if I was going to relate these three diagrams, a person of just dropping an object or tossing an object into the air, as long as these objects travel the same height, so we're just assuming that from the top of the highest point to the bottom of the lowest point, if this is all, let's just make it easy and say it's 10 meters tall, the velocities at the top of all of these, assuming that these are at the same height, would all be the same. And at every given second on the way down or on the way up, the velocities would also be the same. So let's just say, for example, down here, the velocity is 20 meters per second. The velocity launched out of this guy's hand when he tosses it into the air would have to be 20 meters per second, regardless if the object's going straight up and down at a slight arc or at a larger arc. So it's kind of like this equal and opposite trend. Or I could pick a spot in the middle, maybe this is 10 meters per second, and assuming it's at the same height here or the same height here, it would also be going 10 meters per second. So more precisely, if we want to try to figure out how projectiles fall to Earth, this is a very classic example of a cannon on the edge of a cliff where an object's going to be launched just horizontally, and then you're supposed to make the path of the projectile. Well, I think we all know that if you launch a cannonball off of a cliff, even though the cannon is perfectly horizontal to the ground, that it doesn't continue on for infinity in a perfectly flat line. The object is going to fall and fall and fall and fall at a greater and a greater rate. So what we do is we break these up into components. So let's just assume the horizontal component, which we're going to call v of x, in this direction is equal to, let's just make it a simple number again, like 20 meters per second. Assuming that there is no air resistance, and assuming there was no gravity, this object would continue on at 20 meters per second forever and ever and ever, as if this was launched in space. So even here, your v of x is still going to be equal to 20, your v of x here is still going to be equal to 20, v of x is still going to be equal to 20, and still equal to 20 at the end. Now, there's one other factor here, now that we're talking about two-dimensional motion. Instead of just having a horizontal component of velocity, we also have a vertical component of velocity, which we call v of y. So initially, right when the cannonball falls out, this vertical velocity maybe would be almost non-existent. Like right as it falls, it hasn't really had time to accelerate at all. But the further it goes down the line, this object will pick up some velocity going downward. And as it goes a little bit further, it's going to fall a little bit further, it's going to fall a little bit further, and then it's going to fall even further. The shape of this path is not a straight line. Oftentimes people think that it's going to be like a linear path of some sort, but the trajectory or the shape of the path of a projectile typically take parabolic shapes. And the reason for that is because the two components, your v of x and v of y, change at different rates. If this stays as my v of x and always equal to 20, my v of y here is going to start out slow. As I get a little bit further, my v of x here, which again, assuming no air resistance, is going to stay at 20. Now my v of y is going to grow a little bit more. And here, pick another spot, I'm going to have my v of x, which is 20. V of y grows even more. And then right at the point when it hits the ground, I have my v of x equal to 20, and my v of y to be even dramatically more. So these will not necessarily change at a consistent rate. So assuming that these snapshots are taken at every 1 second interval, it isn't going to go 2, 4, 6, 8, 10 as it falls. It might go 1, 4, 12, and 50 or something like that. The rate of increase is going to be based on gravity. So if we wanted to calculate this component, we could figure out the seconds, and acceleration multiplied by time would give you velocity, vice versa. But we're under the assumption that there's no wind resistance. However, this vertical component is changing with gravity. It's got to be calculated independently. In example number 2, they give us the scenario of a cannonball again. They say it's launched off a 40-meter cliff. It has an initial horizontal velocity of 20 meters per second. Assuming there's no air friction, they want us to figure out how far the ball will travel. So we know that it's going to come out of here with a v of x equal to 20 meters per second. Now, if this was a one-dimensional motion problem, if we knew how fast the object was going horizontally and we wanted to figure out the distance, we could just take distance and get velocity multiplied by time to get a distance. If it travels 20 meters every second, after 1 second it would go 20, after 2 seconds it would go 40, 3 seconds would be 60, and so forth. But we do not know, based on the information they gave us, we do not directly know how long it's going to take to hit the ground. However, it can be calculated. So in order to do this, we got to do a little bit of thinking. So always list the variables and draw a picture of the information that they give you. All they give us is horizontal velocity and height. The one thing that we really need is time. Time here would solve all of our problems. So if you look a little bit below here where the example is, I have some equations listed, and all of these equations were equations that we used in free fall. So doing two-dimensional motion is really nothing more than doing one-dimensional motion twice and combining the pieces together as need be. So what we're really looking for here is the time. And the equation that we have for time has variables of height and g, the acceleration of gravity, which we all know. So in this situation, I'm going to plug in the variables that we've got, and I'm going to go from there. So for the object falling from 40 meters, I'm going to do 2 times 40 times the divided by the 9.8. And if I plug this in, 2 times 40 is 80. If I divide that by 9.8 and take the square root of it, it gives me 2.86 seconds. So that's the time it now takes to hit the ground. Our equation for velocity is distance divided by time. Therefore, to figure out distance, you just simply do velocity multiplied by time. Well, the distance could be vertical or horizontal. In this situation, we're talking about the d of x, which is here. You will see we'll use a lot of subscript letters to explain if we're talking about the horizontal or the vertical force. But in this situation, we're looking for d of x. Therefore, we need to use v of x. So our v of x, or velocity horizontal, that this started out with was 20 meters per second. And they tell us that the time it's going to be traveling that distance is 2.86 seconds. So if we multiply it all out, it gives us 57.2 meters, which would actually be the range of this projectile. So that would be one way you could figure out how far horizontally the object is going to travel based upon that height given. The equations that are listed here, you guys can certainly feel free to keep these in mind. You'll probably have to use them in the future. But again, these are all a review of what we've used in the past. Moving on to circular motion. So circular motion also falls under the category of two-dimensional motion. It has a whole different set of equations, many of these which are brand new, And when we talk about projectiles and circular motion, they do kind of go hand in hand because really some objects that are considered satellites that orbit other objects in a large scale, such as the Moon or the International Space Station orbiting the Earth, they follow a lot of these principles, and they in some ways kind of act like a projectile but just on a much larger scale. So here's some new equations that we haven't used yet. Centripetal versus centrifugal acceleration is equal to velocity squared divided by r, and using Newton's second law, we can apply force centripetal is equal to mass times acceleration centripetal, which basically is mass times acceleration, with our acceleration being v squared over r. Important concept here to understand is the difference between centripetal and centrifugal force. So forces act in pairs, remember Newton's third law, and when something turns a corner, there has to be a force pulling them toward the center. But if there's a force pulling toward the center, that means there's kind of an equal and opposite force pulling outward. So the force that's pulling outward is centrifugal, F-U-G-A-L, and basically this is sometimes known as the inertia of the object, otherwise known as the reaction force. Basically what it's saying is if this force pulling toward the center were to be cut, this object would want to continue on in a straight direction, hence the inertia that the object already has. The force that actually does keep it going in a circle, which is pulling it toward the middle, is centripetal force. So I try to remember this one as pedal, like pedaling a bicycle, kind of circular. The centripetal means the inward force. So it's always center seeking. So it's wanting to pull it toward the middle. If you were to attach a ball to a string and you spun it in a circle, the string pulling it in toward the center would be considered the centripetal force. Now, to do calculations with some of this stuff, you're going to want to list variables and equations just like we do with everything else. Other common things to know, which could be implied, is if we ever want to figure out velocities and we want distance and time, when you're dealing with circles, the distance around circles is known as the circumference. So sometimes they won't directly give you that information, so you have to use a little bit of geometry to try to figure out what is the circumference around a circle. So C circumference is equal to 2 times pi times r. And if you wanted to figure out the speed or velocity of an object, speed, I know the velocity is changing direction, but the speed, the total distance divided by the total time, you would do 2 times pi times r if you were only given a radius to find the distance around. And if we can figure out what the period is of orbit or rotation, then we should be able to figure everything else out. So in example 3, they're asking us to try to figure out that if an object is moving at 2 meters per second around a circle with a radius of 4 meters, has a mass of 6 kilograms, what is the centripetal acceleration and what is the centripetal force? So just like any other circular motion problems, you guys are definitely going to want to list the variables, and you're also going to want to list the equations. So look at what they give us. They give us velocity of 2 meters per second. They give us a radius equal to 4 meters, and they give us a mass equal to 6 kilograms. So the first thing they ask us to solve for is the centripetal acceleration. So acceleration, centripetal, is equal to v squared over r. So this is our equation from up above. So we simply only need 2 things here. You're going to plug in the 2 squared, and we're going to divide by the radius of r. Now the numbers here work out pretty easy, but we're just going through the steps. So I got 2 times 2 on the top, which is 4, divided by 4 just gives me 1. And our units will be meters per second squared. And then they're asking us to figure out force centripetal, which is nothing more than the mass times the acceleration centripetal. Acceleration centripetal is 1, and our mass is 6. So our force centripetal is nothing more than 6 times 1, which gives us 6 newtons. So this would be equal to the centripetal and also the centrifugal force, if you think of it in terms of equal and opposite directions. In example number 4, we're trying to figure out how fast an object with a mass of 3 kilograms would need to be traveling in order to produce a centripetal acceleration of 20 meters per second if it was traveling in a circle with a radius of 5 meters. What would be the centripetal force? So a few variables we want to list. Let's list anything that they give us. They give us the mass. They give us the acceleration centripetal, and they give us a radius. So this is what they give us to start with. Mass is 3 kilograms. The acceleration is equal to 20 meters per second squared, and the radius is equal to 5 meters. So, first thing it wants to figure out is the velocity. Well, the velocity, though not directly given to us in an equation, acceleration centripetal is equal to v squared over r. So we should be able to multiply both sides by r and then take the square root of both sides. So we're just using some algebra to solve. So if you're actually trying to find a velocity, you've got centripetal acceleration multiplied by r square rooted is going to equal the velocity going around the circle. So this can solve our first problem because we know centripetal acceleration and we know r. So we're simply going to do 20 times 5 square rooted. 20 times 5 is 100, and 100 square rooted gives us a nice 10 meters per second, which will now be equal to our velocity. The second part is asking us to figure out a centripetal force, and force centripetal is equal to mass times acceleration centripetal. So we already know the centripetal acceleration is 20, and we know the mass is equal to 3. So I'm going to simply put in the 3 kilograms, and I'm going to put in 20 meters per second squared, which is going to give me 60 newtons. With some of the work you have this week, you guys are going to do a lot of simulations. So there's going to be a little bit of math involved, but more of it's going to be concepts for this week. So when you play Angry Birds or when you use the projectile simulator, we're going to try to focus a lot on how projectiles react being launched at different angles and with different gravitational forces attracting them toward the Earth. So if we assume no air friction, there are some magical things that work with certain angles. Of course, the steeper that you launch an object, the longer it will be in the air, but the less horizontal velocity it will have, therefore hindering its total range or distance that it can travel. The greatest angle, or the angle that will give you the greatest projectile range with a given velocity. So if you have a velocity set at a 20 meters per second and you had to pick an angle to launch to try to accomplish the greatest distance, 45 degrees will always give you the greatest distance for a set velocity or set air standards. However, if you have objects that are launched at higher or lower angles, if you go the same distance above or below 45, for example, 60 is 15 above 45 and 30 is 15 below 45, 60 and 30 will land in the same place. 60 will have more hang time, but 30 will get there quicker. So, and you can do this with all sorts of combinations of numbers, 15 and 70. You could do 1 degree and 89 degrees and vice versa. And in theory, it should all work out to be the same. So when you guys go to start the assignment projection of Angry Birds, if you guys open up the document and make a copy, you will find that there is 2 different links here. One is a copy and paste, and the other one actually has the hyperlink that you can go to Angry Birds space. The whole idea here is just for you to explore a little bit about how projectiles work. Even though this is kind of a fun game, it has a pretty good representation as to how objects orbit and how gravity pulls things in circles without being real heavy on the math. So basically all you do is go to the website and play through Angry Birds and answer some of the questions based upon what they give you in here. When you open up Angry Birds space, it will look something like this. If you have difficulties loading this, you can maybe search. There's a lot of free versions of Angry Birds space, but please make sure you're playing Angry Birds space, because when you do get inside of some of these levels, the whole idea here is that you guys see how objects orbit. There is a zone of gravitation that I call it. It's kind of this bubble where if you launch the birds outside of that zone, there is no gravitational field, therefore you will see the effect of a projectile without a centripetal force pulling it in. And if you launch objects too fast and vice versa, how it would go. So you go over here, you try to launch the planet, try to adjust different angles and try different velocities and different masses of birds, and just kind of have fun with it. Nothing too serious, but there are, again, some important concepts for you guys to recognize. So play through 5 or 6 levels if you make it that far, and enjoy. There's also a second assignment that is an online activity. It's a projectile motion simulator, which again, if you open it up, it will ask you to make a copy, and you guys will plug in some information into the simulator based upon what is inside of the document. When you open the projectile motion simulator assignment, you guys will be asked to make a copy, and there's a link here to get to the actual simulation, which I'll show you in just a minute. And you will see inside the lab that there's various trials, and a lot of information is already given to you, like initial velocity, launch angle, air resistance, and so on. And then there's a bunch of blank spaces down below. In the simulator, it looks something like this. On the right-hand side, you can change the input velocity and the initial launch angle. And you can have air resistance either on or off, which I'm telling you to keep the air resistance off. You can adjust these numbers using a slider, or you can actually click on them and type in the angle and the initial velocities. I recommend doing that because it's kind of a pain to try to get this exactly on 50 or 60 when you're dragging it around. But let's just say, for example, you pick your initial velocity and your launch angle and air resistance is off. You hit the fire button. It will show the path of the projectile, and most of the information you're getting, or the readouts, comes from here. The time taken, the range, the height, and the final velocity. So when you guys go to answer these questions, as long as you're using the simulator, take your time and make observations, you should be able to get most all those answers correct. If you have questions about it, you can certainly feel free to email me, but again, enjoy and have fun. This is kind of working in toward the relationship between angles and initial velocities, and how far and how high and how much hang time you're going to get with different combinations, but you do not necessarily have to do a whole lot of math for this. So it's just a starter and a way for you guys to hopefully have fun with what you're doing. Other than that, thanks a lot and have a good week. Take a look. Take a look in the announcements. There are some other things to do this week. This is all I have stuff for the video. You will want to review the notes or save the notes. Those will not be graded, but you will want to use those for some of the practice problems that you're going to have to do later also. So again, thanks a lot. If you guys have questions, feel free to contact me, and have a good week. Thank you.